general relativity, step by step. Last time we evaluated the Riemann-Christoffel curvature tensor in the case of the linearized Einstein field equations for the case of a weak gravitational wave. And we evaluated it in the transverse traceless gauge, which gave us a whole bunch of simplifications for this expression here, where we had zeros all around here, and we only had 4 non-zero components with 2 degrees of freedom, which I called alpha and beta. And we evaluated the Riemann-Christoffel curvature tensor, which only had these 4 non-zero components, which is great. Now, why did we want that? Well, it was a long time ago. It was because we needed the Riemann-Christoffel curvature tensor to tell us the local tidal acceleration or tidal effect of a passing gravitational wave. In one sense, the tidal acceleration is 0, because as I argued with the fish tanks, that if you have a fish tank in a gravitational wave, there's my fish, I'm a very happy fish, but there's my fish in a fish tank, it won't be sloshed around by the passage of a gravitational wave. The fish tank is following a local inertial. The fish tank is in a local inertial frame, so it doesn't experience any acceleration. So the acceleration is 0 from that perspective, but we were making the observation that there were long-range non-local effects going on, which were quantified by the Riemann-Christoffel curvature tensor. And I've got screencast 35 here, and here's my formula. We were looking at the acceleration of a transverse vector n in a particular coordinate system, which was equal to this formula here. And look, I've used alpha here, and I think it should be here as here as well. And I've replaced that with a gamma. So we'll just rewrite this equation in our notation here. I'll pinch in a little bit. Oops, maybe not that much. Okay. So we said d2n by d, and remember there's no distinction between dt squared, gamma. Remember there's no distinction between time and proper time in these coordinates. Equals minus r. That gamma was that gamma. That should be a t. T nu t times n nu. And we'll remember that n was a vector taking one particle here to another particle here while the gravitational wave did its work. Okay. So now we're in a position, now because we've got the rules here, we can just substitute for it. So d2n by, let me pinch in a little bit here. Do that again. d2n by dt squared, component, this is going to be gamma equals x equals minus, and I'll take the minus sign out, r, no, I'm going to leave it in. It's going to be minus r, gamma equals x, t, and then I'm going to expand nu into 2 terms. The only terms we've got are nu equals x and nu equals y. Because last time, when I made up this table here, I observed that we only had these 4, 1, 2, 3, 4 non-zero components. So I've only got 2 components to consider. Let me just zoom in a little bit on that. X, t, n, x, minus, well, I guess it's plus, minus r, t, and now nu equals y. So substituting in here, we've got a nu equals y, t, what's upstairs? It's going to be x upstairs, n, y. And what's the next one? We've got d2n by dt squared y, and this of course corresponds to gamma equals y equals minus r, and then we've got y upstairs. Here we had x upstairs, now we've got y upstairs, t, x, t, this is nu equals x, n, x, plus minus r, y is upstairs, t, y, t, n, y. Right, well, when we evaluated this expression, we had this complicated thing, which I'm just going to call, oh god, what it's varying. I'm going to call it v for varying, where v, go down here, v was equal to minus omega squared over 2 times the real component of e to the I minus omega t plus omega z. So that's the oscillating component, v for varying, equals, let's see if I can get this right. What am I going to do? All I'm going to do is substitute for these terms here from this matrix here, from this set that we did a few minutes ago. Okay. So that's alpha, let's write it out, it's d2n by dt squared component x equals alpha times nx plus beta times ny. This component here is d2n by dt squared component y equals from here x and x gives me alpha. Remember we've got this beta and minus alpha, so that's the x and the y, that's the x and the y. And I'm stuttering because I've got an x and an x, which is this alpha, which is that alpha. I've got an x and a y, which is beta. Here I've got a y and an x, so that's going to be a beta nx plus, actually it's going to be minus, isn't it? Because it's the other component, it's the minus y term, minus alpha ny. Let's just have a look at that. So that gives me an expression for the tidal accelerations due to a weak gravitational wave. Whew, this has gone on far too long. This is 7 minutes, and I don't like them being too long. So what I'm going to do is I'm just going to marvel at the simplicity of this. This is a nice simple calculation. What I'll do is I'll interpret it in the next screencast. Stop there. Stop.